Hi everyone, welcome to another UTIG discussion hour. So today we'll have Nick Montiel giving the talk. So Nicholas is a geologist, planetary scientist, and PhD candidate here at UTIG, and his research interests encompasses geological processes in the Mantle, supercontinent cycles on Earth, and the tectonic evolution of terrestrial planets. He uses 2D numerical models in concert with traditional geological observations, seismic imaging, and remote sensing. So we're going to hear all about that right now. So please take it away, Nick.
All right. Yeah. Thanks, Ed. All right. So can I minimize?
Yeah, if you go
More. Where is it? High video panel? There we go. Okay. So thanks, Ed. So this talk is kind of encompass a paper that I've been working on, and the preprint for that came out as of yesterday. So I'm very, very happy that that finally is available. So we're going to be covering, like the title says, how the mantle is deforming and what processes are occurring in the mantle during continental breakup, specifically at Magma-Poor margins. And we're going to be, this talk is going to cover some of the previous geological literature, and then present new results for seismic reflection experiments in the Ivory Coast, and then also some numerical modeling results about high temperature detachment faults in the mantle during continental breakup. So let's get into it. Next slide. Oh, do I got to click on the thing? Oh, there we go. All right. Aha, there we go. Okay. So yeah, so the big motivation for me is that I really understand planetary evolution for terrestrial planets, including on Earth. And on Earth, that means the supercontinent cycle. And the part of the supercontinent cycle that I'm really interested in are the extensional aspects of it, especially the opening, like you just saw, of the world's ocean basins and the breakup of continents. And that poses a lot of geological and geophysical problems that are very interesting to me. One of which is the sheer variability of continental rifted margins or passive margins. So in red, we have our classic volcanic margin, which is one end member along which we think about continental rifting, the other end being a non-volcanic or Magma-Poor margin. So volcanic margins are exactly what they sound like, covered with, very thick kilometers of volcanic clastics, incredibly magmatic. They tend to be associated with large igneous provinces or hypothesized mantle plumes, like the Parana-Etindeca igneous province in the South Atlantic, and then, the plume responsible for Iceland and the far north. On the other end, you have non-volcanic margins or Magma-Poor. The classic one is Iberia, Newfoundland, but there are other examples all over the world. These are, again, what they sound like. Very little volcanism. There is magmatism, just not very much. And you tend to have exhumed mantle. And these are especially enigmatic and what we're going to be focusing on. So here's what the two archetypes kind of look like in seismic. At the top, you have the Uruguayan volcanic margin, and the key features that stand out are that you have these reflectors down here that generally dip towards the continent. These are perturbed to be faults or shear zones that dip away from the rift axis. Also, very characteristic are very thick SDRs, seaward dipping reflectors that form these packages of volcanic clastics that dip towards the rift axis. And you also have this fairly deep bright reflector that is the moho, and then this really complex region in between where it's very difficult to interpret. And then here's the East Indian Magma-Poor margin, which has very different physical characteristics. You don't have these continentward dipping faults. Actually, you have quite the opposite. They dip towards the ocean. You have this very bright reflector that looks like it's associated with exhumation. It's bringing peridotite or the serpentinized mantle up towards the surface, and then you have a little bit of a volcanic edifice out here, and then you transition into oceanic crust with a relatively shallow moho down here. Volcanic margin, so Magma-Poor margins are what we're going to focus on because there's a lot that's enigmatic about them. In our classical view of our Magma-Poor margin, it looks like this. There's not a whole lot of information on what's happening in the mantle. What is the structure of the ocean to continent transition, like that when you go from continental rifting to continental drifting? They're literally called the rift to drift. So, there's all these kind of mysteries of like, okay, what's happening at the transition? What's happening at depth? What's controlling the structures? What role is magmatism playing? Because even with Magma-Poor, magmatism is present. And that's really important for these larger questions of like what drives continental rifting, because at Magma-Poor at volcanic margins, at least, right? Rifting is relatively easy to explain. You have widespread magmatism and diking, which will weaken the crust as the fluid pressure inside all those dikes and magma bodies pushes outwards and lowers the overall yield stress. Basically, if you integrate the stress with depth, the yield stress with depth, you get like the strength of the lithosphere. Reduces that, allowing it to rift. Well, at Magma-Poor margins, you don't have that. And so what ends up happening is that the yield stress for your continental lithosphere is an order of magnitude larger than available tectonic forces. We know that rifts happen anyway, so there's some mechanism that has got to be weakening the continental lithosphere. And no matter how you slice it, here's different types of continental lithosphere: quartz diabase olivine, quartz diorite olivine, quartz olivine, and then here's our oceanic, just for comparison. The majority of the strength of the continental lithosphere is in the mantle. And the older that lithosphere gets, the more extreme that becomes. So when you have like the South Atlantic opens up through the Pan-African orogeny, which by that point is like 400 million years old, it poses a pretty, that's a pretty big obstacle. It's a cold mobile belt that should be pretty strong. Why is the South Atlantic opening there of all places? And so that's why I want to understand Magma-Poor. The mantle is the key to everything. All right, so this talk's going to be in like 3 different segments. I'm going to follow the 3 different ways that I like to I'm investigating this problem. One is to look at where you have fossilized drifted margins that are preserved near the surface during continental collision. So here in green, you have the Alpine Tethys belt, where the Tethys Ocean has closed. In parts of this mobile belt, you actually have parts of rifted margins that are preserved as ophiolites in small segments. So I'm going to show you 2 examples from there. I'm also going to show an example from where the Ural Ocean closes here in red. You can also examine these rifted margins in situ. So one part of this talk is going to be presenting 3D seismic reflection results from the Ivory Coast, which is an intermediate to Magma-Poor margin right here, where it happens to be blank on this map. Also, I'm going to be presenting some numerical modeling results. And all of these are kind of going to converge on the same set of ideas. First off, we're going to look at some of the ophiolites. This is the Lonzo Massif, or Lonzo peridotite body in the Western Alps. It's an ophiolite that preserves a section of the Tethys rifted margin. So this green area here, this is all peridotite, and where the continent would have been to the north. The seafloor spreading center would have been to the south. So if we kind of zoom in on the northern part of that body, we look at this. You have, the big standout feature is this high temperature detachment fault that is running through the peridotite. You have relatively undeformed peridotite to the north, partially serpentinized, and you got undeformed peridotite to the south. But then along this band, you have a progression from fine-grained porphyroclastic peridotite up to proto-mylonites, up to actual mylonites, up to ultramylonites. Chemically, there's all kinds of evidence for melt refertilization in that shear zone, but also that the southern part of Lonzo to the south of this detachment fault, and what's essentially the footwall, is more melt infiltrated than the northern part, suggesting that these are parts of different tectonic regimes. And the normal interpretation of this is that the northern body is representing the subcontinental mantle, and the southern part of the body is representing the suboceanic mantle. So this is the ocean-continent transition at depth in the mantle. And it's marked by this high temperature detachment fault that is associated with melt infiltration. And more than that, there's also structural weirdness happening. So here I have drawn out where some of the foliation is, just to kind of make it more clear. But you can see that they're not all subparallel to each other. There's all these weird twists and turns, and they form these sigmoid shaped blocks that I'm going to be interchangeably referring to as anastomose blocks or extensional duplexes. But really what they are is that in this high temperature detachment fault, the shear zone isn't really a plane. It's this really complex braided anastomosing structure. And in 3 dimensions, it looks like that. And it's not just, you know, here, it's also down here. And I didn't really draw it out, but there's also examples of it up here and up here. And it's not just Lonzo that shows this. If we move elsewhere in the Tethys margin, we get to Mirdita in Albania. This is the Mirdita ophiolite. The important things here is that here you have basically mapped out the moho. So it's continental material here, mantle material here. But you have myelinatinized plagioclase peridotite, regular plagioclase peridotite, high temperature regions associated with this fault, and all of the foliations also appear to show these sigmoidal structures, like here's one here, and then one here, and then one out here, and in here as well. So it's very, very similar to Lonzo. And if we move outside the Tethys, ocean margins, we move to the Ural Ocean. Here's the Norali Massif and the Ural Mountains. And while the high temperature shear zone is chopped off by the main Uralian fault right here, what you do have is you have highly deformed, myelinatized plagioclase peridotite with complex foliation that indicates, anastomosing shear zones, grading into dunite and then gabbro. So your paleo spreading center would be over here. So this is the beginnings of oceanic crust. And foliation and faults in this proto-oceanic crust all dip away from the spreading axis. And those are the key things. High temperature detachment fault, that's anastomosing. You get melt infiltration within this, as indicated by the plagioclase peridotite chemistry. And the foliations and the faults tend to dip away from the paleo spreading axis. And keep that in mind. And then keep that in mind as we move into looking at the next part of the talk, which is the 3D seismic experiments that were done at the Ivorian coast in West Africa. Right, so we're zooming in on this area here, the rectangle. It's what it is. It's a intermediate to Magma-Poor margin sandwiched between the Romanche fracture zone and the St. Paul fracture zone. So it's this tiny little segment of divergent margin in between 2 big transform margins. And what's really cool though, is that the data here is really, really pretty. Here are 4 lines going through it. You can kind of see the inset down here. So 1 is at the top. It kind of says this weird squiggly thing across the entire area. 2, 3, and 4 are a bit more rational. But what's really interesting is that all of these kind of show these very key features where here you have continental crust and continental lithosphere. So green is your syn exhumation, syn rift sedimentary rocks. Purple is your pre-sediment. Brown is your continental basement. And then in green, it's kind of hard to see, but in green here, you have your these seaward dipping detachment faults that soul into this very bright reflector called the M reflector. And this M reflector here is really the contact between continental material and the mantle below. And then over here, if you move over to the other side, here you have layered oceanic crust. There's your pillow basalts, your layer 2A. Here's your sheeted dikes. Oh, where'd the mouse go? Yeah, there's your sheeted dikes down below. And then here are your sheared gabbros. So that's your layer 2A, 2B, and 2. Yeah.
What's the depth on this seismic?
Yeah, okay. So are you talking like depth to the top of the sea floor?
I just mean like fully like where we
Oh.
see that mantle at.
It goes down to 12 kilometers. That's the bottom of the section. Yeah. So, fairly, like not super deep, but fairly deep. And because this is Magma-Poor, like the mantle is shallow enough that you start to see some of the fine features. And that's what's actually really exciting about this, is because this oceanic crust is actually cut through by these out of sequence detachment faults that go the opposite direction, but they don't soul into one single bright reflector. Oh, what did I do? Previous. There we go. Okay. They don't soul into one bright reflector, they soul into multiple decomons. So you have one up here and one down here, up here, down here. You get 3 here. So this one, and this one, and then here you have 2 here. So you actually have, again, these sigmoidal looking, extensional duplexes in the mantle that look a lot like the high temperature detachment faults that we saw in the Texas rifted margins and the Ural ocean margins.
You wouldn't have this in the magma rich case.
I'll get to that at the very end of the talk. Thank you for spoiling the plot twist at the very end. Yeah, we'll get to that. But yeah, so you get these same high temperature detachment faults that are very similarly structured. And also in these, you have these bright squiggly reflectors that look like sheared gabbros. So this is very much looking like what you would expect to see, what you also see at like Lonzo or Nerali. And then if you kind of zoom out more holistically, this is the 3D top basement surface where the mantle is going to get the contact with the crustal material, oceanic or continental. The big things that stand out are this huge dome that looks for all the world like a mega million. We're calling this like a mantle core complex, even though it doesn't actually breach the surface. But that's essentially what it is. Where is it? Yeah. And then you also have these features over here. And if you map it out according to the cross sections, in white, what you have are the crustal detachment faults that all soul into that single decomont. And then the red, you have the out of sequence detachment faults with the opposite orientation that soul into those multiple decomonts with the extensional duplexes in between. And what you notice here is that they are oriented, that the outer sequence faults associated with oceanic crust are off from the spreading direction. And that was weird. We didn't notice this until very late in the project. But one of the things that I was thinking about is, well, okay, well, you're sandwiched in between the St. Paul and Romanche fracture zones. Maybe this is acting like a big like dextral releasing bend in this overall transform system. The problem is that when you map it out, like if you blow this up, make it transparent and line everything up, they're perpendicular from where they should be. So there's something else happening that's changing the stress regime. That means that the faults aren't opening perpendicular to the spreading direction or opening in line with what you get from a releasing bend. What I think is happening is that the upwelling asthenosphere and melt is coming up in irregular bodies, and that's changing the local stress regime. So the faults aren't, orienting themselves properly. So to kind of like summarize this section at the top, so we start off with in the distal margin with these seaward dipping attachment faults that partially exhume the subcontinental mantle. These get overprinted by these out of sequence detachment faults that develop at the ocean-continent transition, and that these soul into multiple decomonts. They form these anastomosing shear zones, and then since magmatism is increasing as you go closer to the as you move seaward, what ends up happening is that in the footwalls of these out of sequence detachment faults, you form layered oceanic crust, here's the drawing that my collaborator Mantle Massini made, showing that exact process. You're going from this asymmetric crustal detachment fault system to this mostly symmetric system that produces C4 spreading. And keep that in mind as we move on to the next segment, which is the numerical modeling results. I'm not going to spend a whole lot of time talking about how the numerical model works. It's just a little bit of background. Developed in 89 by Kundal et al. It's time marching, explicit, finite volume. It's kind of been used and modified and evolved over the last 30 years to do all sorts of two-dimensional geophysical simulations for the lithosphere. It's not really good for anything, like large scale magnetic convection, like aspect would be. But the important thing is that we have a quartz crust, an olivine mantle, and that we've included nominally anhydrous melt production and also melt crystallization. So we can model magmatic accretion. We've also included dynamic grain crystallization and grain size reduction, and that is what allows us to model high temperature mantle shear zones and detachment faults And that's mostly based on observations and modeling of the Southwest Indian Ridge, which is a slow spreading ridge. So you are exhuming mantle up near the surface. So that's the observational constraint on that aspect of our model. And using that, we explored this parameter space. The key things here are that we're mostly staying in the cold mantle area, 1300, 1350, and 1400 degrees of mantle potential temperature. That's because we're looking at magma-poor margins and we don't have melt extraction. So volcanic processes are kind of beyond this version of flak. So we're trying to keep things realistic by sticking with the magma-poor side of things. We also changed the initial surface heat flux from 45 up to 75 milliwatts per meter squared. 45 milliwatts per meter squared would be something like a craton, or would be like something like a continental craton. 55 could be like a cold mobile belt, like the Pan-African orogeny that I was talking about earlier. Or 65 and 75 would be like younger mobile belts up to like actively extending, lithosphere. So we see kind of like run the gamut of like thermal age. We also have two different extension rates, 1 centimeter per year and 2 centimeter per year. We end up with 19 models. Here's one of them. I'll talk more in depth about what this model is showing, but I just kind of want to train you all so you can see what you're looking at. The brown is continental crust. The gray is the mantle lithosphere, the subcontinental mantle. That's all, olivine. The black is the asthenosphere. Red are those high temperature shear zones in the mantle, and the green are shear zones and detachment faults in the crust. And then in a moment here, the purple starts to show. That is our melt production, and it's going to go from purple to orange to bright yellow. And then in a moment, what's going to happen is that these small yellow dots are going to start showing up in the asthenosphere. That is what, there they are. That is where we actually have active, that's where we have magmatic accretion and melt intrusion. So that's the formation of new oceanic lithosphere. Again, I just really want to stress this. We don't have melt extraction. So we're not forming any basalt lavas at the surface. We're not forming any dikes, which are going to affect the structure. So as soon as we get to this point where the asthenosphere is exhumed near the surface, we just end the model and say, all right, cool. We hit C4 spreading. Anything beyond this, we need diking and volcanism to model it properly. And that's when we kind of stay at our magma-poor regime. So we're going to take this model. We're going to. There we go. Okay. So here's the model kind of zoomed in for 2 million years, 4 million years, 6.5 and 8 million years. And then the next slide, we'll have the rest of it. So you've already seen what's on the left. On the right, it's strain rates. So areas where it's black are where you have higher strain rates. So you can actually see the structural evolution of the system. The key things to point out are that you have these high temperature shear zones that form at the center, drip, and then they dip away from the rift axis, and that these are kinematically connected with the detachment faults that are in the crust. And that this coupling allows you to really efficiently attenuate and preferentially thin the mantle. So you're upwelling this asthenosphere, which is increasing decompression melting. And then as this melt is pushing up from below, you have this, you go from the symmetric system to this really complex asymmetric system with really complicated fault geometries. You start to form accreted oceanic lithosphere as well towards the end. And in the next slide, yeah. Oh, okay, it went away. Cool. All right. Where was I? Right. So you started to accrete more mantle lithosphere. Oceanic lithosphere. You've started to accrete more of that. And as you get close to C4 spreading, all the deformation suddenly localizes. And then as the melt comes really close to the surface and the asthenosphere reaches the surface, now instead of having your rift kind of being driven by like gravitational collapse, so all the faults dip inwards, now they're starting to dip outwards because you're pushing up from below. And then, then you have at the very end, now you've hit true C4 spreading. And we kind of end the model. Because we don't have dikes, you have a hard time localizing once we hit that, which is why you have two different ridges in our model, because there's really no diking. So that's one of the big caveat emptor moments of this whole presentation. But everything up to that point is all relatively realistic. This is a lot to throw at you real fast, but we're about to explore the parameter space. All right, I'm gonna basically what this is we're looking at different features of the model, of all of 19 models compared to full spreading rate, mantle potential temperature, and surface heat flux. So these top two are showing mechanic oceanic lithosphere thickness and melt fraction. And unsurprisingly, with increased spreading rate, the lithospheric thickness goes down and the melt fraction increases. And that makes sense with like decompression melting, right? Is that, you know, your mechanic lithosphere thickness is determined by your temperature. So if you're, you know, if you're spreading faster, then, you know, you're going to have hotter stuff more shallow. So you're going to have a thinner mechanical oceanic lithosphere. Melt fraction is also going to increase because you're getting more decompression melting. Similar story with mantle potential temperature on this side with an increase in melt fraction with increased temperature. No real surprises there. What's actually interesting is when you get down to spreading rate. So this orange anastomosing blocks, that's like the number of these extensional duplexes. So you go into each model, you count up every single one. They tend to decrease with a increased spreading rate. They also the degree of asymmetry. So the width of one flank compared to the other flank, that drops off with increased spreading rate as well. And then if you move to heat flux, you know, in orange, these extensional duplexes decrease with heat flux, and there's also a similar trend, though it's weaker, with mantle core complexes. I don't know if that signal is real, considering there's only 19 models. But this does kind of seem to suggest that, like, okay, so surface heat flux controls the strength of the lithosphere in a big way. So if you have a weaker lithosphere, you get less complexity. So maybe that's what's happening. If you go to like, so we're going to show you one end of the parameter space, we're going to show you the other end of the parameter space. This is the cold end, 1 centimeter per year, 1300 degrees C for your potential temperature. And then we have 55, 65, and 75 milliwatts per meter squared. You don't have that much magnetism happening. There's a little bit of, actually, there's no magnetism at all at the top one. You have a little bit of magmatic accretion, but not a whole lot, but you have a lot of complexity in these high temperature detachment faults. You form these really complex anastomosing blocks, you have widespread serpentinization, all kinds of interesting stuff is happening. Just the complexity goes way up. But then if you go to the other side, this is 2 centimeters per year at 1400 degrees C for the same, you know, heat fluxes, 55 to 75. A lot more melt. The complexity is still there, but it's not nearly as prominent. You tend to get more symmetrical looking continental rifts. And you have also like very widespread magmatic accretion. And also that magmatic accretion tends to be focused in the footwalls of these shear zones, right? Because as you're, you know, upwelling more asthenosphere, you get increased decompression melting. So you're going to get more accretion. So that's all very interesting. And if you zoom out to all of the models, so everything up at the top is 1 centimeter per year. Everything at the bottom, so the top half is 1 centimeter per year. The lower half is 2 centimeters per year. So this is that boundary line right here. As you go down in each of these, that's increasing mantle potential temperature. As you go to the right, it's increasing surface heat flux. So you can actually see, you know, the increase in magmatism with temperature and spreading rate. You can see the decrease in complexity, the increase in asymmetry. You can also see the change in lithosphere thickness. It's thicker at 1 centimeter per year versus 2 centimeters per year. So there's all sorts of interesting, you know, stuff to untangle here about how heat flux and temperature and extension rate all control, you know, the structure of these rifted margins. But tying this back into the geology. This is the Ivory Coast again. It's just in different colors for reasons. This was actually my own interpretation. I did as training, but of the same area. But the key thing is that, so we've shrunk it down. So it's the same scale. So 100 kilometers in one is the same as 100 kilometers in the other. What's cool is that you can see, you know, here you have in the continent this these seaward dipping, especially if you're these seaward dipping crustal detachment faults, where you see them here. You have this domed mantle where you have the domed mantle. The complex anastomosing faults are in here. They're in a slightly different location. You also have increased magmatism, right? Of like the increased melt intrusion of the yellow dots here, and they're in red down here. The big difference is that one has volcanism, real life has volcanism, the model does not have it, which is a huge difference. You don't form any layered oceanic crust here, which might be a reason why all the anastomosing stuff happens here in the model, and it's out here in nature, because this is where the magmatism is happening in real life. So that's, big caveat is that, we have no melting structure, we have no oceanic crust, we have no SDRs, but it does seem clear that this high temperature detachment fault is important to control the structure of the rift to rift transition. So when we think about, okay, so we're lacking melt extraction, but if we think about what role that would play, when we combine all this stuff together, we come up with this conceptual model, starting from the bottom and kind of going up on that picture. What you start off with at first are this relatively asymmetric crustal detachment fault system that is coupling with these shear zones, high temperature shear zones in the mantle. That coupling allows the preferential upwelling of the preferential attenuation and thinning of the mantle. You get upwelling asthenosphere. And that upwelling asthenosphere creates decompression melting. That decompression melting causes the asthenosphere to push up even more. And you end up with the symmetrical continentward dipping system of anastomosing high temperature shear zones near the surface. And the footwalls of these things, this increased magmatism creates your layered oceanic crust, and you get seafloor spreading. And this isn't exactly a new idea. Actually, an early version of FLAC from '98 has a similar thing for mid-ocean ridges. That, at a certain point, you could have magmatism pushing up from below, change the orientation of these faults. But this is, I didn't know about this until recently, but this is kind of like a resurrection of that idea on like a much larger scale for a completely different setting. There we go. And then we can use this conceptual framework and we can put some of the previous stuff, we've talked about into context. So, we already talked at length about how the Ivory Coast kind of fits into this idea, right? It's the whole transition from continent all the way to oceanic crust. But like Lonzo Massif from earlier on in the talk could be a down section, deep part of the ocean continent transition where you have this high temperature shear zone being preserved. While other parts of the Tethys margin, like Air Plata, which I didn't really talk about, but really what it is, it's exhumed mantles with sedimentary rock sitting on top, could represent a higher up section and shallower part of the same margin. Aha, all right. So future work, and this is where the high temperature detachment gets involved with the crust stuff. So this is preliminary stuff that Luke and I were working on, where we can kind of do melt extraction, we can simulate diking. So we actually do create SDRs. So here is the real seismic profile from the Pelotas volcanic margin in Brazil. Here are your SDRs, these bright reflectors up here. Here's the very bright Moho. And then in between, you have this really complex area of lower crust that's very difficult to interpret. And you have your continental material over here. This is essentially the same model that we've been talking about before, except now we have melt extraction. So we're creating what's essentially SDRs, like volcanic clastics. And these lines are isochrons. So everything in that line was deposited at the same time. And what you get is like, okay, you get something that kind of looks like what you get with the SDRs, but then you get this weird inward curve where it looks like you have like lower crustal flow flowing away from the rift axis, and it kind of lines up with these high temperature detachment faults in the mantle. And there's also this high temperature detachment fault at the base of the oceanic crust. It's kind of hard to see because the melt and the shear zones are the same color, but this isn't melt. That's a high temperature detachment. So what might be happening is that this complex region right here might represent an area of lower crustal flow. And that's an area that we're excited to kind of get into with future stuff. One of the other projects that I'm working on, here we go, is one of the other projects that I'm working on is I'm working with Ian DL and Ian Norton in kind of combining their plate reconstructions of Gondwana lands breakup with our own experiments, trying to look at like, okay, how does heat flow affect the weakness of continental crust, continental lithosphere over time? This sort of get an idea of like, how can rifts propagate through old cold lithosphere in response to, like slab suction or upwelling plumes. So how do quantifying those forces, trying to understand how rifts propagate and what, in these high temperature detachment faults are what heat flow can do to affect the strength of the continental lithosphere, and explain why Gondwana land in particular broke up in supercontinents in general. And then taking these models and then just going to a whole other planet. I'm also using FLAC to do tectono-magmatic modeling on Venus, specifically looking at the coronae. So up at the top here is Artemis Corona, which is this. Then here's Hong-O Corona, which is this here. Three different types. This has been hypothesized to actually be a subduction trench of some sort with some sort of volcanism and extension happening in the middle. This is a slightly smaller corona with this really clear annulus of fractures and all of these shield volcanoes and pancake domes in the middle. And understand these things are everywhere on Venus. So understanding where these things come from is kind of important to understanding what is the global tectonic system on Venus, whether it's still active or was active in the past. What is happening there, because Venus is a very useful comparison to Earth, similar composition, similar size, wildly different types of geodynamics. So that's what I'm doing with that. Here's some preliminary stuff that I've been working on with respect to that. Oh, only one of these is playing. There's 4 videos here. I'm just gonna play them all. All right. So basically the top one is like phase. So that orange is like a diabase crust. The blue is where you have widespread melting all over the base of the lithosphere. And you're slowly going to create, this accretionary, bit of a Venusian crust. The row below that one that's labeled magma fraction, that's where you have diking occurring. So the magma comes up, pushes up. So that's where you can kind of see like where is the melt accumulating in the crust. Below that, you have strain rate. So you can see where you have strain rate. Unsurprisingly, it's associated with the diking. And then stress on the crust is interesting because it's showing that all the stresses are happening on the edges, on the outside of where you're accreting all of that new crust and all that new lithosphere, which might explain this annulus of fractures and even the subduction for the larger coronae like Artemis and Quetzalcoatl. And that is the end of, dang it, I was going to be smooth. All right, so that's the end of my talk. Happy to answer any questions. Also, as of yesterday, the preprint for all this became available, so please go check it out. And it's also on my ResearchGate. The better version is on my ResearchGate. The formatting on Authoria got weird. But yeah, so thank you so much.
I have a question.
Yeah.
So like from what you showed in your model result, between a magma-poor and a magma-rich margin, it's really a spectrum, not really.
Yeah, it's absolutely a spectrum.
Can
Yeah.
you place other margins within that spectrum?
I
or
think
in
so.
nature, is it more of really this kind of
Okay, the reality is it's probably going to be way more complex than whatever I say, just because you have heterogeneities, pre-existing fabrics, all that kind of stuff. But what I think is generally on the first order happening is that in the volcanic margin, you have lots of melt super early on. So those faults that dip away from the rift axis happen super early. And that's why you have the SDRs that grow this way. You have, the faults moving like that. You also have mid-crustal flow accommodating that, going this way. And that's why you have a super bright moho, which is also not just a moho, it's probably a detachment fault of some sort. And then on the other end, you got the Magma-Poor, which I just explained. So like Ivory Coast, which is Magma-Poor to intermediate, has SDRs. It's probably could be placed in between. So the more intermediate you get, it's like this balance of like, okay, how early does this out of sequence detachment fault occur? And when does the magmatism occur? Because if that all happened late, then what you end up with looks like a Magma-Poor margin.
And the magma-poor will generally be more asymmetric.
Yeah, it'll be generally more asymmetric. Yeah, I think so. I think it'd be generally more asymmetric. And that would kind of make sense with like Iberia and Newfoundland because I don't know. Iberia and Newfoundland's weird. Yeah.
Can you tell me how the diking takes it from one ridge to the ridge? How does it like localize?
Right. Yeah, so without the diking, what you end up with is you end up with, like clockwork, 2 faults or 1 fault like that. And because that, if you have 1 fault, then yeah, it's going to localize there because you have 1 weak zone. But if you end up localizing with 2 faults, then in the model, right, because there's no, the model is just going to go like, okay, these are the 2 active spreading centers, and they're just going to slowly migrate away as you're upwelling more asthenosphere. If you have diking though, that creates a new weak zone in 1 spot. That is weaker than either of those 2 faults. So these faults will shut off, you'll create new faults, but it'll always be localized over the diking, which is very weak.
Thank you.
Yeah.
So you're using heat flow essentially as a proxy for possible age.
Yeah.
You in like the beginning setup of your models, you change the continental crust thickness with the heat flow?
No, we kept that constant, mostly because if we started varying that, we go from 19 models to like 150.
Oh yeah.
So it was one of those things, like we had other plans, like, oh, I wonder how volatility affects it. And just, the number of different, the size of the parameter space just ballooned. So at some point we were like, okay, what's more important? Do we want to change heat flux? Do we want to change lithosphere thickness or mantle potential temperature? And yeah, so yeah, that's a long way of saying is that we basically kept all of the crust at like 35 kilometers across all of it.
I'm gonna go again.
Go again.
So then with your, like the older continental crust,
Mhm.
you're talking about like, cold mobile belts, but with cold mobile belts, like in something in the East Africa Rift, there is like pre-existing weakness in
Yeah.
those. So did you consider
It's
adding any of that?
well, so that new project I was talking about, of trying to understand their propagation, one of the things that we added to the models, we did add suture zones. We basically just took a line of serpentinite, put it at like a 45-degree angle, and did from top to bottom to go like, okay, this is where 2 continents, where like 2 parts of a craton got sutured together or something along those lines. And we were looking at, okay, what is the force required in the model to break that apart? So it's something we're considering for the next part of our for basically like chapter 2. But that's probably very like you said, this, like it's very important for rift propagation. Like it probably follows pre-existing weaknesses because for the most part, this Atlantic follows the Pan-African, and then it suddenly jumps across the San Francisco Craton, which is super cold and strong. Why did it just go around it? It cut right through it. So there's something happening there, and I think what it has to do is that like out ahead of the propagating rift, you have thinning asthenosphere that is allowing heat to propagate up. So out ahead of the tip of your propagating rift, you have elevated heat flow. And I think that might be something. That's something that I'm actively investigating right now.
Cool.
Yeah.
I'm wondering how you go from your like sort of nice 2D rifting to Venus, where it seems to be like a circle.
Well,
So,
that's the thing, is because honestly, the circular thing makes it easier.
right, okay.
Because what happens is that with the circular thing, essentially it's a 2D slice that just is symmetrical about every single axis. So you don't actually need 3D to study it, because every single cross section you draw is going to be more or less looking the same, at least for some of the coronae. Some of them look like they have a hinge, but a lot of them look mostly symmetrical.
Okay. But surely as you go further out of the circle, you'll have to have some kind of
Yeah,
in
sure.
that direction as well. Or
Yeah, there are. So some of the coronae, and actually a lot of the coronae, what they do is like, so you have like the center, which is flat, you have pancake domes, other shield volcano looking structures. Then you have this annulus of fractures around the outside, and then outside that annulus, you have radiating fractures, right? So then once you get far enough away, you're right, there is a 3D aspect. But that 3D aspect isn't that difficult to explain. The more complicated and interesting bit, at least to me, is like what's happening where you're accreting new crust in a circle in the center.
that's cool.
Yeah.
For the work offshore Africa,
Mhm.
you were talking about it maybe being like a releasing bend.
Yeah, that was one of the.
It could be like, those could just be antithetic structures, so that would make sense if they were sort of at a high angle to the synthetic
I'm
structures.
just wondering about that, if they could be antithetic, but antithetic structures, but I couldn't I couldn't figure out a way to like, really figure that out because we were kind of limited to that one study area. We don't have 3D access to everything else. So those are like the only faults that we could see. Like, yeah, they could be antithetic structures if there was something else outside of our field, that would make more sense. But you're also talking about antithetic structures that would have to go across, like continental crust, the proto-oceanic to oceanic crust.
It's really
So
hard for this.
yeah, and like it could be, it was harder to explain and harder to kind of like wrap our heads around. And so we thought that like, okay, if you have these irregular magma bodies coming up affecting the local stress conditions, that's a bit more testable, at least with our limited amount of data.
Yeah. Well, you can just see it with the extension or the stress directions, if it makes sense. in their orientation.
Yeah.
Cool.
Do we have any online questions? Or
Yeah, any online questions on Zoom?
Hi, can I ask a question? Can
Yeah.
you hear me?
yeah, I can hear you.
Okay, cool. I was wondering, like, when you have like the 19 models, when you change like the temperature of the mantle and like some other parameters, I was wondering if the model is like high resolution enough for you to like study the behavior of the fault. For example, when you increase the temperature of the mantle, does it change like how the fault ruptures or like the stress regime?
Yeah, no, that's a fair question. All of our resolution below like maybe like a kilometer or 2 kilometers is worthless. So really like we don't really know what's happening on a fine scale. That's part of the reason why like we did not have melt extraction in the early version, because dikes happen fast and they're really, really, really thin compared to a plate. So until we could figure out a way to approximate that, we just left it out of our models.
Okay.
So it's not it's something we thought about. It's not something that we could really fix. Because if we were to increase the resolution to the point where we could see finer details like that, we'd end up in a different physics regime that'd be a lot more difficult to model. And also running these on my desktop upstairs would take forever.
Computer's right down there.
I don't know. It was kind of like overkill for what we were trying to do. So, also there were like other reasons I wasn't aware of that was like, yeah,